So very good evening, and I'm a little bit early today. So a warm welcome to the first lesson on where we are trying to find out the basics of quantum field theory. So those who are watching this video or will be watching the video maybe later, you are all welcome. So this would be an episodic video through which we will be actually, all the basic concepts of quantum field theory. So I just started a little bit earlier because there are certain concepts and ideas which I just wanted to, make sure before we go ahead and start with the today's class. So this program or this class would be primarily basic building on the basics of quantum field theory. Okay, so those who are watching me, can you just put me a yes or no that whether I am audible or not? But sometimes there is some kind of an audio problem which comes in. So am I audible? Can you just put a yes or no? I think I'm audible, right? Okay. So, in the first phase, what I would like to define, I was talking to one of the subscribers today in WhatsApp, and he was very enthusiastic and he was asking me that, sir, what are the things that I need to know in order to become or in order to do mathematics on theory of everything? Now, I told him that actually theory of everything means you actually need to know everything. So that is how the theory of everything. So you need to know general relativity, quantum mechanics, a lot of mathematics and stuffs like that. So quantum field theory is one of the candidate theories in order to find out what is called a theory of everything. So this is like string theory. Quantum field theory is also one of the theories which starts or which strives to find out, which tries to find out what is called a theory of everything. This is one of the theories, although there are many other theories. Now, before I go ahead, I would just like to share my screen and I would like to show you in general, in the concept of physics, we all know that what is a field. So I would just go to the very basics because these are not generally explained. So if I've got a kind of an area over here, okay, for example, and I have got a vector, I have got a vector which is pointing around here. And also I have got something which is called a scalar. Okay, I'm sorry for my handwriting because I'm using my mouse. And we have also tensors. Okay, so we have also got the tensor. So, in general, when I talk of what is a field, if I ask you that, tell me what is a field in terms of physics, then obviously you would tell that in case of a field, I mean to say the physics part, not the mathematics. Mathematics again, field is something different. So if I tell that, okay, tell me what is actually a field in physics. So you might say that in physics, a field is a physical quantity, right? Just like this, which is represented by a vector. It has got a scalar and it has got a tensor. So these three things actually make up what is called a field in terms of physics, right? And it is represented that has a value for each point in space and time. That means, for example, if I take my this figure, so if I take, okay, let me take a fresh one. So if I take a kind of an area, say for example like this, then this particular point, for example, will have a value. This particular, say for example, v1, this particular place will have a value v2, this particular place will have a value v3. So each point in space, this is important, please note that each point in space is actually marked with a value. So every point in a space is marked with a value. It can be either a vector, it can be a scalar, or it can be a tensor. So this is what we call in general is a value. So for example, if I take this to be a weather map, now say for example, I take this to be a weather map. Okay, I call it as a weather map. Okay, I call it as a weather map. And this map is something like this. So each point in space, say for example here, okay, let me take a zone. If I take this zone, or if I take this zone, or I take an abrupt zone like this, then each point will have a vector pointing around here. Say, for example, the wind direction, it is pointing around here, and here it is pointing around here. So this part of the plane, which is pointing around here, I can call it as a field. This part of a plane, I can call it as a field. This part of a plane, I can call it as a field. So this is the concept of what we call field in physics. So I can say from here that the surface temperature is described of that weather map is described by a number which is assigned to each point in the map, and the temperature can be considered as a certain point in time which will change as the temperature changes, right? So assigning an arrow, if I assign an arrow as I've shown you to each point in the map, this map will show basically a speed S, for example, and a direction D. So which part it is pointing, this is S, this part is pointing, this is D. So this will be basically assigning what is called a speed and a direction at that point. And this is an example of what is called a kind of a vector field. We call it as a, where is my pointer? Yeah. So this part, if I take this zone, sorry, if I take this zone, then this is called a vector field. So let me call it as a vector field. Okay, let me draw new. So this part of the zone, if I have got arrows like this, this is what is called as a vector field. Okay. Now this vector field, as you can understand, it can happen in weather, it can happen in fluid dynamics, it can happen in wind direction, it can happen anywhere. So this is what we call is the concept of a field. I hope you can understand. Please do respond sometimes yes or no. Otherwise, I feel very uncertain that whether people are listening or. So a surface wind map which has got arrows in each direction which describe the speed and the direction at the point is called a vector field. It can have different dimensions. If you have different dimension, that we take it as a tensor field, etc. Now this same thing, say for example, which is pointed in this direction, which you can see. Now, if I have a point, then it can go like this, like an arrow, and it can be an electric field. If I get a point like this, then it will be going like this, which can be B as a magnetic field. This is basically the concept of field. Now, why I'm mentioning one point is important, that whenever I get a spread over data or information, and if the arrows are pointing in this direction or whatever the direction, it can be pointing in this direction also. When I get a spread over like a data like this, and I am trying to consider all those components of that particular set, we take it what is called as a field. This is the concept of the field. So that is how we start that field, and basically the what we call as the classical mechanics is different. We will come to that point. So imagine that in classical mechanics, a billiard ball. Okay, let me show again this part of the screen so that it will become. I have not started with the actual slides because this is pretty important in order to make you understand. So that is why I'm making you understand about this. So in the case of a billiard ball, say for example, this ball, it throws a force over here. For example, force, if I take it, then this ball throws a force over here. Here you see that there is no spread, right? Each and every ball. So for example, object 1 throws a force on object 2, and it has got a kind of an acceleration, and it has got something like that. But the moment we say that, okay, there are many billiard balls, 1, 2, 3, 4, 5, and 6. And this is actually something which is spread over an area. So this is spread over an area. That is the moment we take the concept of field. So classical mechanics and field theory is different, is that we are not considering individual particles, but a spread over particles. And we will see in quantum field theory that this is the field which is important. The particles are just manifestations. They just are considered to be excitations of the field, right? So classical mechanics are considering particles individually. They have got an individual velocity, individual acceleration, individual momentum. but in case of a field, as I have shown, it is a spread over the objects, and that is where the concept of field emerges. Okay, can you just tell me that whether you can get me or not? How the optical theorem works? I don't know what is that. Uh, Let us concentrate on what we are talking. Then, otherwise, again, I have to go some point or other, and the main class will be lost. So, first of all, as I was telling, that as we move up the ladder, so whether it is mathematics, science, economics, physics, etc., we nicely explained, sir. Okay, who is this? Nadim Iqbal. Okay, you got my point, Nadim. I'm so thankful. So as we move up the ladder, as the complexities emerges, as machines emerges, we always try, now we are always trying to make things pretty simple. We will start with what is called the evolution of quantum field theory. As I told you, this is what is called a theory of everything. So what is everything? That means we are trying to put all the theories in one single equation or one single theory. That is called quantum field theory. So here you see that earlier we were cavemen. Okay, we used to hunt different places. Then we started building instruments for hunting. Then we took shelter in the caves, and we started worshipping the forces of nature, and we developed instrument for hunting. So what happens is that also you see that how the evolution of automobiles have started, right? So I have a theory which can relate quantum mechanics and GTR. I'm not sure. Okay, SSG, what you can do is that you can later email me, right? I can put up your research paper on ResearchGate if it is truly peer reviewed, and if it is fine, then definitely you can do that. But right now we are concentrating on learning quantum field theory, which is not a very easy task to do. So I am just putting all my effort today to make a episodic ideas of quantum field theory, right? So we can talk about those things. You're absolutely welcome. You can email me. You know my email, so that would be great. So also you see that eating style also has changed. The automobiles have changed. So everything, I mean to say, every part of the evolution and the concepts have changing. And do you notice one a very important thing is that with the change and with the evolution pattern, things have started to do what? Things have started to become very small. This is also important, that things actually have started to become very small. So with the when things started, when things start to get small, what happens is that we reduce the size also. You look into that the televisions, how it was, and now it has become a smart television. So in this way, all the evolution pattern actually, started to develop in certain ways, and things started to become very small and small and small. So here you see what happened is that now that we know that there are, with the evolution of human mind, we saw that there are fundamentally four forces which exist: gravity, strong force, weak force, and electromagnetism. Now, because all these forces have different kinds of theories, all these forces pertains to different kind of concepts and mathematics, we are trying to get all these theories together. So gravity with strong force, with weak force, and electromagnetism, we are actually trying to make into one single grand unified theory. Here, I would like to take a pause. Why? Because I don't know whether you know it or not. If you can let me know in the chat box. Can you tell me who was the first person who found out the first unification? Can you tell me that who was the first person to find out the first unification? If you know, please put it in the chat box. I would love to know that. Who was the first person who first created the first theory of everything? It was not Richard Feynman, it is not Paul Dirac. Many, many years earlier. Maybe Einstein? Well, partly, yes, but I would say it was first Isaac Newton. Now, Newton's theory of gravitation, that formula F equals to G, actually first united the laws of motion on the earth and of astronomy. So before Isaac Newton, everybody thought that the planets and the orbits and stars and everything, they follow a different set of rules. Okay, and the people walking, the cars rolling, everything around on the earth, they follow a different set of rules. When gravity was found in a single equation of Isaac Newton, this was the first time, which is called the first grand unification theory. That means gravity is actually behaving in the same way on earth, and the same laws of motion, the Kepler's planetary law, etc., actually are basically from the same Newtonian mechanics. That was called the first unification theory. And the second unification, can you tell me who was the person who found the second unification theory? That was James Clerk Maxwell, who first united electricity and magnetism. Okay, so we are actually now, the entire science and research around the world is to find out a theory of everything. Enough is enough. The scientists are telling, okay, enough is enough. We have so many theories, so many mathematics, so many complications. Now let us unite that into one theory. That is called one single theory, grand unified theory, which Stephen Hawking, etc., great scientists are trying to do. Now here comes the basic idea that you need to now know. I think, yeah, I have explained this in my video called string theory. This grand unification theory has several parts. So these are called candidate theories. One candidate theory is gravity with quantum mechanics. That is called string theory. One candidate theory is gravity with gravity with electromagnetism with special relativity. That is called quantum field theory. Another is searching for what is called a loop quantum gravity. So ultimately the aim is the same. The aim is the same, that how to find, but different approaches are coming together. But ultimately it would lead to the same answer, right? So here you see that when we talk of quantum field theory in theoretical physics, what do we mean? It is remember, it is a theoretical framework. Now you might ask, sir, why it is a theoretical framework? Why it is not a scientific framework? Because till now, all the assumptions of quantum field theory has yet not been experimentally proved. Yet it has not been experimented. We will come to that. You might ask me what? I will tell you. So that is why it is called a theoretical framework that combines three things: classical field theory, special relativity, and quantum mechanics. Now hold on. Here I have to make you understand that what do we mean by classical field theory? Remember, classical mechanics and classical field theory are not the same, my dear. Okay, classical mechanics is taking the laws of Isaac Newton, Principia Mathematica, whatever has been framed, that is called classical mechanics. Or you can take astronomy, that is called celestial mechanics. But classical field theory is a totally different subject. I can talk on that, but this is not the right platform. So classical field theory is something, as I told you, those billiard balls, when they're taking a single area, when all those are taken into together, that is called classical field theory. And in classical field theory, what is the mathematics that dominate? Can anybody tell me? Very simple. What is the mathematics that rules classical mechanics? Classical field theory? Can you tell me? Classical mechanics, we know Newton's three laws of motion. What is the mathematics? What is the mathematics called, which is ruling, which is the most important thing in classical field theory? Any idea among those people who are watching? What is the mathematics? Calculus? No. No. Classical field theory is basically dominated by Lagrangian and Hamiltonian. Calculus is already there in classical mechanics. We are doing differentiation, integration. But when we are using classical field theory, remember, those billiard balls are no more one billiard ball. Maxwell equations, yes, to some extent, but that is what we called the Lagrangian and the Hamiltonian. We will see that why Lagrangian and Hamiltonian is important. Because classical field theory is no more using individual velocity, individual momentum, individual acceleration. It is not being used. Are you getting my point? Please ask me questions. We are not trying to imagine that it is not a billiard table which has got single balls, which has got velocities. It is a spread. It is an area, and we have to calculate the total area. That means we cannot talk of individual differentiation integration. What we have to do, we have to take the Hamiltonian, the total energy of the system, the total Lagrangian of the system. Are you now clear? Let me repeat, it is not individual billiard balls. ISER aptitude test is very close. Any good wishes for the aspirants? I don't know. Yeah, ISER aptitude test is very close. I know. But again, this is not the right platform. Please ask me questions related to this. Otherwise, when people watch this live stream later, I also lose the interest. So are you getting my point? Whenever we are moving into a field theory, an area where individual particles are not being taken, that means individual differentiation, individual integration, individual velocity is not important. What is important is the total energy of the system. That is the Lagrangian. The total energy T minus L equals to T minus V, that is the total Hamiltonian. That is why remember, whenever we are moving into field theory, we need what is called the Lagrangian and Hamiltonian. So classical field theory, as I told you, plus special theory of relativity. Obviously, we need special theory of relativity and quantum mechanics, all of them taken together. Now, you might ask me a question, sir, why they are not taking general theory of relativity? I will come to that. Quantum field theory is not taking into account general theory of relativity. General theory of relativity is GR plus quantum mechanics, that is string theory. But quantum field theory is considering special relativity, classical mechanics, and the quantum mechanics. Okay. So also remember one thing, that gravity or Newtonian gravity is also considered to be a field theory. I will talk about that later. Peskin PG291 mixing path integral as well as sign convention. I need to check it out. Anyway, so it means that classical mechanics is dominated by Lagrangian and Hamiltonian mechanics. Newtonian mechanics is that. No. Yes. See, I mean to say, you can use Lagrangian mechanics into and Hamiltonian in Newtonian mechanics also. But the thing is that where I will use Lagrangian, where I will use Newtonian mechanics, that depends upon the problem of the system. So classically, it is dominated particularly by Newtonian mechanics. Newtonian mechanics is the real classical mechanics, yes. But classical mechanics is not dominated by Lagrangian, SSJ. I am taking that classical field theory primarily uses Hamiltonian because it is the total system which is considered, not the individual particles. It is the entire zone that we have to take. You got my point. So that is what classical mechanics is different. Is there a theory which combines GR and QFT? It is on the way. I mean to say, the physicists, the scientists have not yet found anything. But general relativity is not combining with quantum field theory. General relativity is being combined with quantum mechanics. Quantum field theory is quantum mechanics, special relativity, and classical mechanics. But general relativity and quantum field theory, there is no attempt to combine. Right? The reason is that because general theory of relativity is being combined with string theory. Right? Special relativity is being combined with quantum mechanics. So GR and quantum mechanics, both of the combinations, still we have not been able to found. Okay. Okay, so let me go back to what I was talking about. So here you see why it is being done, because it helps a unified description. That means all the fundamental forces except gravity is taken. Quantum field theory is not considering gravity because it is coming to be very problematic. There's a lot of problem considering gravity. So the scientists have discarded, gravity. Yes, there are a lot of technological advancements which have come, okay, including now particle accelerator. You might ask, sir, why particle accelerators and quantum computing is considering quantum field theory? Juan McLaren has quantum gravity and attempt to GR theory. Yeah. Okay, so now the thing is that you see that why particle accelerator, give me a little bit time to explain. I will show you later that whenever these cosmic rays are being studied, whenever things are accelerated in particle accelerator, it shows that it is creating new particles and anti-particles, electron and positron, right? Particles and their complementary anti-particles. And remember, when this was invented in cosmic rays and anti-particles, quarks and anti-quarks, quantum mechanics did not have a mathematical framework how it could describe the creation and annihilation of the particle, the creation and destruction of the particle. This was the basic reason why we needed quantum field theory. I will tell you, don't rush right now, otherwise you will we will get confused. We'll get one by one. I will explain each and everything. All your doubts will be cleared, but give me some time to make a slowly step-by-step approach. Okay, so interdisciplinary application, because in condensed matter physics, superquantum conductivity, quantum Hall effect, these are all using quantum field theory. Okay, so definitely there is a need of technological advancement, and there is a need for unifying all the big three theories: Newton's theory, Einstein's theory, and Planck's theory or quantum mechanics. Is it all clear till now, all of you, those who are watching? I know there are many people who are watching and there will be more later. Is it all clear? Can you put a yes or no, just like SSJ have done? I will be happy. Okay. Now we come to what is called, why do we need a quantum field theory? Or you can say that what was the problem? What was the problem with the earlier theory? Okay, only SSJ is responding. Are the rest of you, are you feel boring, or you know all those things? Do let me know. I'm very open kind of a professor. So the problem is that what were the problems in the earlier theories? Okay, Durgadas, Dragos Dodi. Okay, so what was the problem? There should be some problem. Otherwise, unnecessary. Why we are creating problems? All clear. Okay. Why Polyakov lecture on string theory is hard to follow compared? I will come to those questions. Just let me finish, because this is again, you are telling of string theory, we are talking of quantum field theory. This will create a confusion. So what was the problem? Definitely there is a problem. Otherwise, why we would need suddenly a new theory? So this part of our live session will clear you practically, that when you talk to your friends or when you study later, you will actually can find out that, okay, this was really the problem. And that is why we need, so until you understand the problem, the solution won't be clear. So here you see what I have told, that earlier there was the Principia Mathematica, okay, the force gravity described by Newton as action at a distance. Then there was Michael Faraday's, who first coined the term, right? Then we came across Maxwell's equation. The first unification, as I told, was done by Isaac Newton in his gravity equation. Then again, it was Michael Faraday who coined the term field, and then it was Maxwell. So Maxwell again found that electricity and magnetism are not the same phenomena. I mean to say, they are not the different phenomena. Okay, here I would like to take a little bit, because Goat is constantly asking me, do you know that what was the contribution of Professor Ashok Sen? And why Ashok Sen's contribution to string theory is important? I will take another live session. I will clear you out all the mathematics on that. But remember, Ashok Sen's contribution to string theory is another step forward towards unification. The work that Ashok Sen had done, Professor GR, is the last revolutionary theory which describes phenomena in cosmic scale such as black holes and others. Are there any awareness in quantum field theory whose results approach on GR? Are there any attempts made in quantum field theory whose results approach GR on taking limit? Yes, a lot has been taken. I will come to that. Quantum field theory has also started to predict, phenomenon around the black hole and event horizon. Yes, there has been. And it is, again, quantum field theory has nothing to consider with general relativity. So when you're talking of QFT, do not consider GR as one of the phenomena. GR is totally out of the scope of QFT. We are only considering special relativity, classical mechanics, and quantum mechanics. So GR is only related to string theory, which is somewhere related to quantum physics. Okay. So Ashok Sen's contribution in string theory is that whatever he tried to show you in the research is that these two phenomena of two strings are not actually the manifestation of two things. It's the same brain which is actually evolving to a higher dimension force or a string. So that is why Ashok Sen is the only person in the world who has made a significant step forward in uniting string theory and the two strings into one string. That is why Ashok Sen's contribution is very famous. I will make a video later on what Ashok Sen combined, right? So this is quickly, I will skip. You all know black body radiation and Max Planck and photoelectric effect, etc. So then it was Niels Bohr, right? Introduced the atomic structure. Then it was Lou de Broglie and all these Schrodinger, Max Planck, Heisenberg, everybody came together and they formed what is called the quantum physics. So till now, there is no confusion. We have classical mechanics on one way going and we have quantum mechanics. Special relativity has not yet come. We will come to that. You explained very well, sir. Aisha Gilani. Okay, thank you very much. I was actually very excited to talk about quantum field theory because everybody knows that Shaunak means physics for students means general relativity. No, I am very much doing a lot of work on quantum field theory with different people. So you will come to know slowly. Thank you very much. Hello, yeah, Samintha. Hello, very good evening. So I am talking, what I was talking about is that this part is there and special relativity and quantum mechanics is there. Now you see what happens. So the entire Newtonian mechanics has been expanded in special relativity. Any doubt on that? No problem. Everything in Newtonian mechanics is now into special relativity. Length contraction, time dilation equal to density square equals to mass, energy equals to mass, these, that, whatever. Everything is done, right? No doubt. And on the third part, so one, we have Newtonian physics. Second, we have special relativity. And third, what we have? Quantum physics. Now, Newtonian physics problem is solved. Why? Because Newtonian physics is now not Newtonian physics. Every equations from all those have been gone into 4 vector, 4 momentum, 4 velocity, and we have got special relativity, Minkowski space. Albert Einstein has got the Nobel Prize. We are very happy. Okay. And the question is that, so you omit Newtonian physics. Out of 3, 1 is deducted. A question on the topology background, if I may, what would we recommend as a visualized brains, membranes, and p-brains in higher dimensions? Yeah, I will come to that part. I will come to that, but let me not lose the track. Otherwise, the main focus will be lost. We are dealing, let me first cover the initial part of today's video so that people also will enjoy, right? So one, Newtonian mechanics is gone. So what is remaining? Special relativity and quantum mechanics. The question is that, can we now unite special relativity, quantum physics into something? What is that something? That something is called quantum field theory. Right? Thank you, Ryan Chan. You are from which country, Ryan? I don't think you are from India. So if you can put it, I will appreciate. So that means that special relativity and quantum physics are the two things which is remaining to be united. Because Newtonian mechanics has already been generalized into special relativity. So that is why now we need only that quantum field theory. Okay. Now remember that there is another which is called electroweak theory, where electromagnetism and weak theory has been united by Abdus Salam, Steven Weinberg. We will come to that part later. As I told you, there is no one theory of everything. Everything has been united in separate. There are many theories. Quantum field theory is one of the theories. Okay. So how do we unite this part? That is the biggest challenge which comes. Okay. Now take a pause, drink a glass of water, because we are now coming to a very important part. Now here you see that initially quantum physics actually is non-relativistic nature. If you have watched my earlier videos on quantum field theory about 2-3 months back, I have actually, Professor, there are still some problems in CM which are still unsolved, such as many body problem. Yes, I'm some four potential. See, Ryan, the thing is that, sorry, tech lover. The thing is that it is very true. These are not from PNP problems. Okay, what you are telling of the of those many body problems. So these are not solved. I mean to say, you cannot Riemannian hypothesis, pure mathematics. These are not solved. I mean to say, what will you do? So that is why I am saying that the search will go on. These are not solved problems. People are trying to solve. Anybody solves, get an award, something like that, right? So that doesn't stop us into making a grand unified theory. These are not solved. So we are moving ahead. Now, what I was trying to tell is that please pay attention that in my earlier videos in quantum field theory, live lectures, you will see mathematically I have derived that Schrodinger equation was basically a classical equation, right? One side is the kinetic and one side is that potential, and it gives the total energy, right? And I have shown that why Schrodinger equation was a classical equation, and from Schrodinger equation you can actually derive back to Newtonian laws, Newton's laws of motion. Now, because Schrodinger equation was classical in nature, that is why the quantum effects Schrodinger equation cannot possess, cannot explain. For example, spontaneous emission. I've omitted, otherwise it would take a long time to do. So any electron which is, spontaneously emitting, it would create infinite possibilities. Electron generating photon, you never can tell that this photon is going to come back to the ground zero state. You cannot. Even if it is a possibility to come back to ground zero state, in the meantime, when it is transiting back, it will lose its energy. So essentially, Schrodinger equation was not a solution to bring a non-relativistic equation, relativistic equation. So Edwin Schrodinger actually framed it based on what is called the classical way. So that was a problem, that how can we get a Schrodinger equation which is relativistic in nature, because the attempt was to unite special relativity and quantum mechanics together. I hope this is clear. Now here you see that traditional quantum mechanics does not incorporate the principles of special relativity. That means if I go back to this slide, that means the union between quantum physics and special relativity is actually a problem which is leading to quantum field theory. Okay. Now, initially there were two attempts. One was the Dirac equation, which was found by Paul Adrian Maurice Dirac, and another was Klein Gordon equation, which was founded by Oscar Klein and Walter Gordon. These were initial attempts. Now, this equation which I have written, this is a relativistic equation. I don't have access to the manuscript where I can get the original non-relativistic equation, but don't take me wrong. These are right equation, but the attempt was to make a relativistic approach, so that relativity and special relativity and quantum mechanics is united. There was a problem. The problem was this, that Klein-Gordon equation, which actually describes spinless particles, which are pions or anything like that, and Dirac equation, which is taking fermions, which obey the Fermi-Dirac statistics, spin-half particles. This, along with quantum mechanics and special relativity, would actually lead into something. I'm talking of that time when Dirac was trying to find out. This is something we don't know. Today we know quantum field theory, but we don't know. Okay. Now the problem was that Klein-Gordon equation actually allows solution with positive and negative energies, which leads to a lot of problem. Now again, you might say, sir, negative energy is a hypothetical concept, etc. Yes, we understand. Quantum field theory itself is a very theory. So as I told you, that it has not yet been experimentally proved, all the implications. So what happens is this, that if we get a negative energy, for example, if the mathematical equations actually show what is called a negative energy, then what happens is that that means if I get an electron that is moving on the opposite direction of the time, which is a problem. I mean to say, how can this happen? The entire physics falls. I hope you get my point. So in physics, energy is what? Energy is a fundamental property. It is either zero or always positive. Now, if I get an electron which is moving in this direction, on the opposite direction, that is a big problem. right? So in general, for classical physics, we have particles which has energy and whatever the mass of the motion. So a negative energy would not correspond to any physical particle we know of. So this is a big problem which happened with Dirac equation and Klein Gordon equation. Is it all clear? Am I going too fast, or anyway, you can just respond. So similar to the Klein Gordon equation, the Dirac equation also have solutions for negative energy. And the good part is that, I don't know, this negative energy actually first predicted what is called an antiparticle, or you call antiparticle. Pronunciation should be antiparticle, I think. So this creation of antiparticle was first proposed by Paul Dirac. And it came out of a problem. The problem was that Dirac equation was showing mathematically a negative energy. And this negative energy cannot happen because the physics will fall down if electron is moving in the opposite direction. But also, it is important that the mathematical derivation of Dirac equation actually led to what is called an antiparticle. And today we know through particle accelerator and everything that yes, there are antiparticles, there are complementary particles. Every particle has got an antiparticle. And this particle and antiparticle, when they collide, they create new particles. This is what is called creation and destruction or annihilation. And can anybody tell me, this is a quick hint, can anybody tell me this creation and destruction or annihilation is being described by a famous person's diagram? Can anybody tell me who was that famous person who first showed that this particle and antiparticle, how they create, and that can be beautifully done in a diagram? You can come from Malaysia. Okay, I do physics outside my job. Please make me your acquaintance. Great, from Malaysia. Absolutely, well done. I should give a love sign. Can I give a reaction? No, I don't. Is there any reaction button in StreamYard? I don't know. Anyway, great. This was Richard Feynman. Richard Feynman was the first person that is called Feynman diagram. Okay. So that was a problem. Now, in order to solve that problem, again, that this is theoretical, Dirac proposed what is called is a Dirac sea. Now, again, this is a theoretical concept, but anyway, it is good that we can mention what is a Dirac sea. So here you see that according to physics principles, particles tend to minimize their energy. So should not electrons be constantly dropping down to these negative energy states? So he proposed that the vacuum is actually a sea of infinitely many electrons, all occupying these negative energy states. All of them are occupying a negative energy state. So he proposed something which is called a Dirac sea. So if there is a positive energy, Paul Dirac told that there is a sea. It is not right. I mean to say, this has got problems also. Interpretation is not correct. So it has got a sea, and all the negative energies or the negative particles are going into that sea. So here you see I have written that a vacancy in this Dirac sea would behave like a particle with positive energy and opposite charge to an electron. Just a second. So this whole remarkably lined up with the properties of the positron, electron and the positron, the antiparticle of the. But it is not correct also. So here you see it is difficult to reconcile with the idea of a finite vacuum, and it is difficult to reconcile with the idea of a finite vacuum energy. And that is why you see that both the Dirac equation and the Klein Gordon equation, they actually predicted that the presence of negative energy solution raises questions about causality and stability. So Dirac sea is not a very good solution. So particles could theoretically transit from lower to lower and lower energy states indefinitely, leading to instability. So it goes down and down into negative energy. Where will it go? So the basic idea, what I'm trying to tell is that now you understand that what was the real reason to bring out a theory. quantum field theory was basically that negative energy which Klein Gordon equation, in order to marry special relativity with quantum mechanics, it was first found that it is leading to problems. And this problem was the negative energy problem, which somehow the people smartly tried to solve it, but it was not. So these limitations led to the development of quantum field theory, which provides a more sophisticated understanding of particles and antiparticles. So today I will take a pause because this is just, we have started. In the next session, what I'm going to tell you is that how this particle and antiparticle creation and annihilation actually happens. And if it happens, then how do we describe it? Professor, I cannot understand causality. Is there any mathematics involved to explain causality? Yes, definitely. There is a mathematics involved into different causality. These mathematics I have ignored, as I have already put it in the thumbnail, that quantum field theory fundamentals for beginners. If you want me, then I can email you the causality mathematics, the quantum entanglement, etc. These are all actually the causalities which are explained in detail mathematics. Okay. So in the next lecture, which I will announce very soon in the next week, starting of next week, we will then cover what is called particle antiparticle creation. And then we will start with the fundamentals, because there are few fundamentals. Let me tell you what we will cover. We are actually covering what is called particles and fields, because I need to show you that what is the background behind Klein Gordon formalism, the physics behind their equation. So Klein Gordon formalism, Ryan, is basically to put a relativistic quantum mechanics, simple. How we can put the equations of special theory of relativity in quantum mechanics, right? So we will take up the field and the particles, because we will show that more than particles, how fields are important. Yeah, absolutely. Thank you. Then we will come to what is called the Lagrangian and Hamiltonian. This is going to take 2 episodes, because I need to show you how Lagrangian actually occupies an important place in quantum field theory, avoiding those very big equations. And then I will tell you what is Hamiltonian, and both Lagrangian and Hamiltonian works. Then I need to talk about symmetry and symmetry breaking. And let me see, what was the agenda? Yeah, and then the interactions and Feynman diagram, what is called a quantization, and important applications of quantum field theory. This is the total agenda of the online classes. So by the end of 3-4 episodes, I can promise you how much group theory I need for quantum field theory. Yes, you need, I would say, a medium level of group theory. But most importantly, for the mathematics of quantum field theory, I will come later. It is quite elaborate. I mean to say, is that similar to the Dirac equation allowing us to discuss? Yes, absolutely, Ryan. You are right on the point. Great. Dirac equation allows us to describe the motion of electron relativistically. You're absolutely right. So was the Klein-Gordon equation. But what we are talking now is that what are the problems of the Klein-Gordon equation and the Dirac equation? That was the negative energy problem. And the negative energy problem actually made a blessing, because we found antiparticle mathematically. But because the negative energy is something which cannot be complemented with Dirac C, right? So that is why we need something which is called a quantum field theory. So that negative energy and infinite, infinity, etc., are something we will see now later, that it is called renormalization. Okay, so renormalization helps to eliminate those infinities and make a consistent theory. Imran Mushtaq, good evening, sir. Could you please how Dirac formulated the gamma matrices full math steps by step? Is Lagrangian or Hilbert space an alternative method to understand Dirac? Thanks. So this will again require a different, a kind of an understanding. See, you are all welcome to ask me question. Obviously, live session is meant for that. But try to understand that when I come after college, so much of mathematics and so much of correction of research papers, then standing for 2 hours giving webinars, Then coming to this, basic idea is to make you understand step by step what is the agenda. So all of you are welcome. You can always send me emails, WhatsApp messages. I will try to respond as early as possible. But what we can do right now is to understand what the agenda is. That in that some sense, it could say that these two equations are different formalism of the same theory. Absolutely. Ryan is right on the track. I'm so much... is group theory lectures by Richard E. Brochures enough? I think so. But again, this group theory, etc., these are again coming off topic. I request what Ryan is doing right now is great, is asking me things which are related to the topic. Now, if you already know everything about quantum field theory, I mean to say, I'm sorry, I'm a simple teacher and a professor. I don't have too much of knowledge to explain you. But yes, I'm trying to explain step by step for beginners who can get an interest in this very difficult subject of QST, because the mathematics, oh my goodness, I mean, those who are talking all those things, if I show you the mathematics and I start explaining, those 20 people will reduce to 2 people. And that I don't want. I don't want young people to lose an interest of the subject just because of the mathematics. So give me some time. With many years of experience, I'm doing this so that I can generate that interest in those young people, and they can take up research in quantum mechanics, quantum field theory, not because the mathematics is difficult, so that they get a good understanding of the subject. Remember that knowing a subject is not knowing the mathematics always. Knowing a subject is knowing the subject. A good teacher is somebody who motivates that you take a very difficult subject. I'm there with you. A good teacher is not who bombards with a lot of mathematical equation and makes your life hell. And I have seen that, I have suffered that. And that is the reason I don't want to do that, to be honest. Right? So this is a step by step. I'm not boasting. Don't take me wrong. Today, I'm talking right in this YouTube live session. You won't find, this type of simple explanations of quantum field theory in any book or in YouTube videos. I mean to say, do you, right? So all those are equations, very difficult, probability density, this, that, crazy cramps. Yeah. So I mean to say, what I'm trying to do, try to please appreciate and please cooperate with me. I'm trying to make things easier for young people who can take up the subject. And for that, mathematics, minimal mathematics is required. And I will show that mathematics when we talk of Lagrangian formalism, right? Is linear algebra and Hilbert space inner product necessary for understanding Dirac's theory? Yes. Imran? Yes. I would say, very good question. Yes. Because for Dirac's theory is a very advanced theory where he is putting relativistic quantum mechanics. Inner product is simple linear algebra. And Hilbert space also comes in basic quantum mechanics formulation. So if you don't know, inner product and Hilbert space, then you don't even know the basic classical quantum mechanics. Don't take me wrong. I'm just saying how you can extend it to relativistic quantum mechanics. These are more advanced mathematics. So yes, if you see my video, what is the mathematics that you need to know about quantum mechanics, I've clearly told. Vector calculus, linear algebra, probability theory. Simple. You need to know probability theory, vector calculus, and linear algebra very well. Then you can do the classical part, the classical mechanics. Relativistic mechanics, more complications and more. That is why I'm telling that you can ask me question, I'm trying to answer. But what I'm trying to do is make the session more and more interesting so that the history and the evolution is much better. Anyway, thank you, Ryan, for asking me so beautiful questions. Thank you, Crazy Cabs. Thank you, Imran. Thank you, Goat. And thank you, everybody. SSJ, Aisha, Samidha Jana, Dragos Doddy, and everybody, those who have been there. So I will soon announce the next part where we are talking of the creation and analysis. So till now, everything is clear, right? How we started, how things went up ahead, and how the grand unified theory, why we want. Till now, we have got 2 theories only. Newtonian mechanics is unified in special relativity. Rudra Sija, thanks. And special relativity is right now trying to get united with quantum mechanics through Dirac equation and Klein Gordon equation. And both of them has predicted a negative energy. This negative energy is counterintuitive, and this negative energy is not matching with your intuitive understanding of physics. So in order to eliminate that negative energy, we need a new theory. However, It is a good blessing that Dirac's equation of negative energy predicted what is the first called antiparticle, and now we know that every particle has got an antiparticle. So in the next session, I have a lot of interest on subject, but you see now, you see this, what I was telling, physics RMR is telling, but maths to make me take a step back. Yeah. So why will that happen? If physics RMR, I think he's a young person. If you have an interest, then you should learn properly, right? Okay. Anyway, so good to go. So I am making a big video series also on the concepts of quantum mechanics. You will find, and also do not miss the 2nd June podcast, where a pure scientist and a pure mathematician, Professor Surajit, is coming on 2nd of June, 8 p.m. Indian Standard Time. And you can ask as many questions regarding mathematics, mathematical career, practical mathematics, I mean to say applied mathematics, pure mathematics, fear of mathematics, everything. He is actually considered as a 2% world scientist as per the Stanford University. One point about the Klein Gordon equation. Yeah, please tell me. I'm waiting for that. Good. I mean to say it's a good amount of participation, and I will keep this happening. I will make sure that in 2-3 episodes we entirely understand the concept of quantum field theory. Then we will move into the mathematics. Also, it is a request to all those 20 people who are watching this that please do not miss my episode on general relativity, because I am now contacting with some German people to read the original manuscript of Albert Einstein, because I don't know German, and they are helping me to translate that in English, and you will come to know the real evolution of general theory of relativity, which I'm sure no YouTube video does, because I am reading those German scripts, I am translating them into English, my people are helping me, and you will actually find out general relativity, the metric tensor, geodesics, Riemann geometry through a story, through a history, through a beautiful narration of stories. The first and the second part is already on. It is called Story of General Relativity. I generally don't talk great things about my achievements, which I should not do. My teachers and professors are told that Shaunak, you should always keep low. So this is the name of my episode, The Story of General Relativity. Watch them, you will really enjoy, because there is a story about Einstein's life, where Einstein has gone, his problem with Mileva marriage, his wife, and how metric tensor slowly. It is fascinating. I got hold of those manuscripts thanks to my German friends. They're helping me a lot. It's amazing. I mean to say, more than making the videos, when I'm reading that, I cannot sleep at night. I get goosebumps that I can really see Einstein on the table and writing those amazing things, right? What was Klein Gordon's reason behind using the square box symbol, the notation? Are there any connotations to symmetry or geometry should be aware of? Yes, very good question. Again, Ryan, you can contact me later, because Klein Gordon square box, that actually has got an automatic relation which is called the symmetry. We will talk about that. You got a very good brain and a very good hint, but again I have to actually open the what I call my writing pad, or I don't have it as soft copy, so I have to show actually, and we will talk about that. Don't worry, I will take it up in the next slide, next session, and explain Ryan's question, especially that why is the square box symbol used. Yes, it has got a relation with symmetry, and that is why Paul Dirac and Klein Gordon equation, when they came into quantum field theory, this actually got extended to Lagrangian, and that has got an automatic relation to symmetry. So Klein Gordon equation, direct relation to Lagrangian, direct relation to the symmetry. And this symmetry and symmetry breaking, spontaneous symmetry breaking, the Higgs, etc., they all have got beautiful relation with quantum field theory. So yeah. So how can we understand the concept said by Feynman that positron is a proton traveling backwards in time? Yeah. Again, this is a very good question, Nadeem. That positron is a proton traveling back in time. This is because, as I told you, that positron is what? The antiparticle, right? The antiparticle. So if the antiparticle, actually, just I showed you here, let me show you, it was actually discussed. So here it is. A negative energy or antiparticle, if it is moving backwards in time, right? Positron is an antiparticle which is actually moving backwards in time. It is the opposite of the, it is the complementary is the electron. So if electron is moving in this direction, in the positive direction, this direction, so obviously positron will be moving in this direction. Because the invention of positron, when Dirac actually did the mathematics, it showed, you see this presentation of mine, this way, opposite direction of time. And that is why the negative energy came in, right, Nadeem? I hope I can make you understand. That is why the negative energy came in. And because negative energy is something which mathematics cannot explain, or the physics is falling, we tried to make a new theory, which is called quantum field theory. So that is why Feynman rightly told that positron is a proton, which is moving, traveling backwards in time. I hope you get my point, right? So it is going in this direction, it is going to this direction. So positron is basically an antiparticle of the electron. So anything which is going in this direction, the antiparticle would be going in the opposite direction. That was basically the formulation of the Dirac equation and the Klein Gordon equation. Anyway, thank you for being with me, and I will announce, as you know, if you have subscribed to my channel and click on the bell and all icon, all the notifications you will get. I put it on the live button on the live section, and you will get it. So just a quick, I would say feedback. All the people who are watching, did you really find it useful? Tell me yes or no. Then I will quit. I'm feeling thirsty. I just came back around 7:40, so I was feeling a little bit sleepy also. So anyway, it's good. How did you find it? Quickly, 2, 3, 5, quick comment in the comment box. Quickly, are you finding it interesting? What is your feedback about today's session? Rudra is saying yes. Anything more? Nobody is writing. See, this gives a kind of a feedback, positive feedback to me. Absolutely, yes, Professor. Tech lover, great. Okay, fine. I understand that. Rest of you, you might not be interested to write, but I understand your participation is really essential. Much appreciated. It's a unique level in intuition I don't find elsewhere. Yeah, this is what I was telling, that this is something which I'm trying to give. So please cooperate with me. I do spend a lot of time, in making those presentation and videos. Maybe I will talk about my personal life, how I manage things someday. You really don't know me, what I do. I mean to say, not that I am a great person, but my illness, my eye infections, my urine problems, that has taken a toll of my health. Very nice in front presentation. Anyway, so I really want someone who could become a friend more than a subscriber. But it is always not delivering lectures, but we come close and we start talking and enjoying good moments together, right? Isn't it? So it is not always that people will look upon me as a professor, but also become a good friend, something like that. Anyway, take care. Goodbye. We'll see you soon, and don't miss the podcast, because it's the first time a good mathematician, a world-renowned mathematician, is a member of the Royal Astronomical Society of London also, to tell you, right? Chalo, take care. Goodbye. Good night.